You know, when I was a kid, there was this commercial on. I was about your age, a very cheesy commercial. And it went like this.
It was so good, I told two friends about it, and they told two friends, and so on, and so on, and so on.
It was annoying, but it got stuck in your head. So much so that they made a spoof about it. If you ever saw the movie Wayne's World, you might have seen this little spoof.
Well, you know how these things start. One guy tells another guy something, and then he tells two friends, and they tell two friends, and they tell their friends, and so on, and so on, and so on. You know how these things go.
So I learned a lot about exponential growth from that commercial. It was kind of an addicting thing, and you would sit to your friends all the time, and so on, and so on, and so on. So it did its job. It was very annoying, and it stuck in your head. But it did show example of exponential growth by doubling the specific equation y equals 2 to the x. In this section, we are going to be studying the exponential growth, but not at just 2 to the x. We're going to talk about many different exponential growths and decays. And the thing to know about exponential growth and decay is you can't start with 0. You have to have something to make something. You have to have people to make people. You have to have money to make money. You have to have money to lose money. So we're talking about growth and decay. And we're going to start with two basic principles here. First of all is the rate of change of p with respect to t is inversely proportional to 5t. Now what does that crazy stuff even mean? This is all that I'm asking you to think about right now. Rate of change of p, what does that mean? That means that p has a rate of change with another variable, and we're calling the other variable t. So p changes over time. We'll call t time, p for population, because it's an easy example to think about. Population changes over time proportional to this little example here. Now this is a very specific case where we're saying it's inversely proportional to 5t. Inversely, so it's reciprocal, and 5t. Now this isn't quite our entire operation here because there's no constant. How does it grow? Does it grow by doubling, by tripling, by going up 4%, by going down by a third? We don't know. We introduce what we call this k value. And that k value we call the constant of proportionality. Now, it's just constant for now, which means if we are doubling something, we are assuming that it always doubles. Now, is that in effect always going to be true? No, but this is mathematical modeling. So we're assuming a situation is true and we're making predictions based upon those events and those numbers. The one that we're going to be dealing with a lot is this one right here, the rate of change of y with respect to t. So how does y change over time? Is directly proportional to y. So here's what it is. If you're going to change your values of y, it all depends on how many y's you have. So again, if you have money, then you get more money or less money depending, assuming it's constant. Now that k is our constant proportionality. So if k is positive, all the values will be going up, exponential growth. If k is negative, all the values are going down, exponential decay. And the case where k equals 0, it's not a part of the equation because if k equals 0, it's not growing or decaying, it's just being a flat line. All right, that's the basics. Let's go on to the first example. We are going to develop the growth and decay model. We're going to start with this, the one we just talked about. Y is proportional to itself. Population, population, money, money, bacteria, bacteria, whatever it is. Okay. Now let's solve this differential equation. And when we solve it, I think you'll notice something. So we're going to divide y by both sides. You get the y's over here. Going to multiply both sides by dt. Remember, k is a constant, so it doesn't matter what variable we're using. So now that it's separated, we're going to integrate it. So this is the natural log of y. equals k times t plus a constant. The inverse is e's, so let's see what happens when we get that. So this is y equals e to the kt plus c sub 1. And as we talked about in the last lesson, when we add the exponents, the same as multiplying their bases. So we're going to call e to the c1 just a giant capital C. And now we have the exponential growth and decay function. Formula, we really should call it. Now, does that look familiar to you? If you remember last year, remember PERT? You usually do it with money. The amount of money you have is calculated by the principal, which you start with, multiplied by your interest rate times how much money you leave in the bank. Look at that. It's the exact same formula. This is where it comes from. So that y equals ce to the kt is the general form of an exponential growth and decay model that fits all models when something is proportional to itself. For example, we're assuming that p is proportional to p, which means that how p changes over time is proportional to how much p there is. I mean, population, you know what I'm saying. Okay, we don't have to solve this differential equation every time, because when we solve it, it's always going to end up being the same thing. So really, we're just using this. So all the calculus is done. The calculus was coming up with this. The rest of this assignment will be using this. So here's just a general generic example. How do we find these things? So we'll take this value. At time 0, there are 250. So 250 when the time is 0. So what you end up with is 250 equals c. Now k times 0 is 0, and e to the 0 is 1. Anything to the 0 power is 1. So we come up with this. It's our initial starting value. That's what the c value is in this function. It's what you start with. We're starting with 250. Now, since we're assuming it's proportional to itself, and we're assuming it's exponential, we only need one more data point to come up with the k value, to come up with that constant of proportionality. So we're going to use this fact. So 400 equals 250 e to the k times 1. And now we solve. We're going to divide both sides by 250, and you end up with, I believe, 1.6. I did all my calculations ahead of time, so I wouldn't waste your time with the calculations. E to the k, and the solve to solve for k, we do the inverse of e, which is natural log. So k is the natural log of 1.6. So our equation really is p equals 250. Oops. Hang on a second. 250e to the natural log of 1.6t. There's our equation. The equation is nice, but we were asked to solve something. We're asked to find out what is p when t equals 4. So what is p when t equals 4? And that's just a flat-out calculator exercise. You just plug that into your calculator, and you get p is approximately 1638. There's a decimal involved, but I'm going to keep it as a whole number because I'm assuming my p is population, and so we're not going to have fractional people. We're going to have whole people. So assuming that this rate stays constant in time of 4, call it 4 days, 4 years, 4 months, there will be this much, starting with 250. So 2 steps. Find our initial starting value, find our constant of proportionality. Once you have the formula, we can do anything we want with it. For example, We got bacteria. This is one of the clues we are given. I should say the only clue, because after we have that clue, then they're asking us to figure out how many are there how much time does it take for the bacteria to triple. So this is a little weird, but it's still the same. It's proportional to itself. Now we got to find C, we got to find K. Well, in this case, we're not given C. We're not ever given an initial starting value. So maybe we can work our way around it. What we know is that it doubles in 3 hours. So in 3 hours, how much do I have? Well, if I started with C, that means in 3 hours, I have twice that much. And there's my equation. Well, there's an equation that can help solve for K. I can divide both sides by C. And I'm allowed to divide both sides by C because I know C is not 0. Because if C is 0, I can't have any growth at all. So there is my equation for K. Inverse of E would be natural log. So my K value in this case is 1/3 of the natural log of 2. So my equation that I have so far is this. 1/3 natural log of 2 times t. Now can I answer my question? The question being, how many hours will the number of bacteria triple? So I didn't really have to know how much I started with, because I'm doubling it and I'm tripling it. So what I know is if I triple my starting value, that's 3C. Divide both sides by C again. And here is my equation. Now I have to solve for t. Well, and I solve for t with all of my great logarithmic skills. And the inverse of e is natural log. I'm going to take the natural log of both sides. All right, now I solve for t. So I'm going to multiply by 3, divide by natural log of 2. So my t value is approximately, let me get to that page, 4.755. And what are we talking about? Minutes? Hours. So it's going to triple in nearly 5 hours. If it does double in 2 hours or in 3 hours, then it will take 4.755 hours to triple. That I know for sure. The puppy weighs 2 pounds at birth. Well, that's good news. Well, first of all, it's a nice healthy puppy. But second of all, I know I'm starting with 2. And 2 months later, the puppy is 3.5 pounds. Now, so why does it interest us to know what the puppy weighs 2 months later? Well, they're growth charts, if you've ever seen them. When my kids were little, they would measure their height and weight every doctor visit and compare them to a growth chart. And the growth charts always looked exponential. They always looked something like this, where the middle would be the average, and then you have extremes. So if you were too far to the either extreme, that told you something about, your child. Is it going to be taller than normal, shorter than normal? Are there any concerns about health, things like that? So they compared them to a growth chart. So we're assuming for a nice, healthy, average puppy, is this a normal growth? Now, we don't know. We don't have a puppy growth chart, but I can tell you, if we know 3.5 pounds in 2 months, I can tell you in 3 months, if the rate of change is the same, what that puppy should weigh. So let's use this fact right here. So 2 months later, the puppy is 3.5 pounds. So my time is 2. My k is my only unknown, so I can solve for k. I'm going to solve for my constant of proportionality. So I'm going to divide by 2. And then the inverse of e would be natural log. So we'll just take the natural log of both sides. And then divide by 2, so that my k value is, I'm going to use a decimal this time. We could say natural log 1.75 over 2, or we could estimate it. Sometimes it's nice to see the k value because, first of all, the k value is positive, so you know the puppy is increasing, and the k value is 0.279. So our equation for this particular puppy would be this. Now, if I want to know how much that puppy weighs after 3 months, I just plug in 3 for t. All right, and whoops, we're plugging in 3. So according to my calculations, the puppy would weigh about 4.630 pounds. So that would be the expected weight. If the puppy's a little heavier, maybe the puppy's eating too much. If it's a little lower, maybe a little bit not malnourished. But that's how we can use exponential growth to figure out expected weight. Now radioactive decay, now you're losing the stuff. The other ones we're gaining, now we're losing. So that k value should be negative, it means they're going down. So it's a long, long problem, but basically what we've got is we have 10 grams of plutonium. So our starting value is 10. Now we gotta look for that constant of proportionality. Well, here's my other fact. It has a half-life of 24,360 years. Now a half-life means half of it is left. So if we started with 10, in 24,360 years, there should be 5 left. And we know our time is going to be 24,360. Now we solve for k. I'm going to divide both sides by 10. And if I divide both sides by 10, guess what? What is 5 divided by 10? It's 1/2. Half-life. Interesting. Alright, again we're going to do our inverse, which is natural log. Natural log of 1/2. Remember, any natural log between 0 and 1, or greater than 0 and less than 1, is negative. Now this number is going to be a little tiny because it's taken a long time to get there. So when I solve this for k, when I divide both sides by 24,360, here's what I get. It is negative, but what I got is 1, 2, 3, 4, and hang on, 2, 8, 4, 5. That's my k value. It's negative, which means it's going down, but it's also very small, which means it's very slowly going down. So my equation is this. Now if you're calculating this, you might do what I did and just store this in your calculator as a variable, which you get a more accurate reading. Here I rounded it. Okay, only going to here I rounded it, so my answer won't be exact as if I carried it out a little bit further. But the question is, how long will it take before I only have 1 gram left? So how long? I'm solving for t when I know I got 1 left. I apologize, up here I need an extra 0. I'll just stick it in there real fast. Okay. So just do my little calculation. Divide both sides by 10. And I take the natural log of both sides, which leaves me with this. Sorry, I skipped a couple steps there, but I divided by 10. And then I did the natural log, that was the inverse of e. So natural log of 1/10 equals this. So my t-value, once I take the natural log of 1/10 and divide it by this number, would be approximately 80,934 years. Now, if you used more decimals, or if you actually stored that value in your calculator and had more accurate, you might have gotten 80,922. We're not really worried about how accurate it is because, frankly, it's just an exercise in learning exponential decay and growth. But you should have gotten over 80,000 years, almost 81,000 years, for that to be one left. That's a long time. A long time. So that's a long time to be shooting off radiation. All right. Enjoy yourselves and take it easy. Bye.